Good evening, ladies and gentlemen. To the UK Minister for Universities and Science, the Right Honourable David Willetts, the Charge d'Affaires for the British Consulate, Tony Brennan, the Consul General for Melbourne, Gareth Hoare, and the Chief Scientist for the Commonwealth of Australia, Professor Ian Chubb, Chancellors, Vice-Chancellors, Professors, Doctors, ladies and gentlemen, welcome to this very special occasion. My name's Paul Willis, I'm Director of the Royal Institution of Australia, and it's my honour to be your host for this evening. An opportunity to hear and interact with a visiting delegation from the United Kingdom about the state of research and development in the UK, and also to compare that to the state of research, development and science here in Australia. If you have a mobile phone, I would please ask you to either turn it off or preferably move it to silent and tweet the proceedings of this evening's event. If you do decide to tweet, could you please use the hashtag #CriticalList. Critical list. And of course, there's always a portion of the audience who have no idea what I'm talking about when I do. Ladies and gentlemen, to introduce our very special guest speaker for the evening, would you please welcome the Vice-Chancellor and Principal of the University of Melbourne, Professor Glyn Davis.
Thank you. We used to have principals at the university, but now we just have vice-chancellors. Can I join Paul in welcoming you all and begin by acknowledging the Wurundjeri people of the Kulin Nations on whose land we meet and paying respects to elders past and present. It's a wonderful occasion tonight, and I'm delighted to have to say a few words at the start, but I want to acknowledge how unusual it is to find a minister who spends every waking hour in the UK worrying about universities and no doubt visiting their campuses and being dragged around to look at facilities, who chooses to fly to the other side of the planet in order to do exactly the same on the other side of the planet. We've been delighted that David Willetts has spent this afternoon here at the University of Melbourne looking at a number of the impressive science-based facilities we have here, first Bio 21 and now here in the wonderful Melbourne Brain Centre in the Kenneth Myer building. This is an extraordinary investment in neuroscience by the university, the state and the nation, and it's wonderful that we welcome you here and that you get a chance to see it here in the heart of the Parkville Medical Precinct. We have a great panel this afternoon. Paul's going to introduce each of them, but I'm delighted to also welcome Ian Chubb to campus, and Margaret Shield, who works on campus, but nonetheless delighted to see her here. To get proceedings started, it's a great pleasure to call on the United Kingdom Minister of State for Universities and Science, David Willetts, to speak to us.
Well, thank you very much indeed for the opportunity to be here today. For me, it's a great privilege to be here at the University of Melbourne. And as you heard, I've already had the great pleasure of seeing the excellent medical research that you do here, and both visiting Bio 21 and also seeing the work that you do in neuroscience. Now, I gather what we're talking about this evening is what's called the critical path. And I guess it's the critical path from the lab, from the University Research Institute, out into the wider world and application and commercialization. At least that's what I want to focus on as the critical path. So let me just set the ball rolling by describing very briefly how we see that in Britain. And I don't know if you kind of worry about this in Australia, but in Britain we rather beat up on ourselves on this. And what we think is we've got good science, very high quality science, we're proud of our science, but somehow when we sort of end the public funding for the science and expect the commercial sector to take on responsibility, that handing over of the baton is like a particularly amateurish baton change by a rather poor quality team in the Olympics. It endlessly gets fumbled and dropped. And the transmission out into the wider world we think is not good enough. And we then beat up on ourselves even more by saying it's because our commercial sector doesn't take risks the way they do in America. If only we were entrepreneurial like they are in America. Instead, our businesses don't take risks like they do in the US, and that's why we have this problem. Well, I have increasingly concluded in my 4 years or so in this post that that is an unfair characterization of the problems we have in Britain, and above all, it rests on a deep misunderstanding of the US. And my thinking has been heavily influenced by the recognition that the reality of what happens in America is very different from the rhetoric. The reality of what happens in America is that public funding and public support for innovation, for new technologies, for the application of science, takes them far closer to market than their rhetoric would have you believe. And this is, and what we were doing is we were stopping funding research upstream. Our research councils were only funding them in research institutes and universities. And we were then expecting the commercial sector to take over at an earlier stage than the commercial sector is supposed to take over in the US. And then we were beating up on ourselves for being risk averse, when the reality was they were doing a better job in America of the public sector and federal agencies and state governments taking and sharing risk than we were doing in Britain. And this goes back to a historic argument in America, when it was founded. Their independence from the UK was a rather more fraught and painful process than Australia getting its independence. But when they had their debates in the late 18th century around what was called the Federalist Papers, what would the new federal state of the US be like? Alexander Hamilton became the first American Treasury Secretary, argued for big, effective government that would create a modern, dynamic, big state, a big economy promoted by the state. And Thomas Jefferson argued for a nation of independent farmers, sturdy yeoman farmers cultivating their plots. And what has happened in America, someone put it very neatly, is America has ended up with a Hamiltonian state hidden behind Jeffersonian rhetoric. And we mustn't be taken in by the rhetoric, we should look at the reality. So that's my policy conclusion. It's therefore completely legitimate for governments to help technologies on that critical path from the research lab to commercialization. Now, as soon as you take on that responsibility, you face a very difficult challenge. The reason why some governments don't like doing it is you have to decide priorities. You can't do everything. When it comes to the science base, the pure science, we let 1,000 flowers bloom. We let the scientific community decide on their priorities. We have a very independent and autonomous set of universities and scientists, and we have scientific excellence across a range of disciplines. Once it comes to supporting technologies, governments have to choose priorities, and it's painful and controversial. But advised by experts in our technology strategy board and in our scientific community, I identified 8 great technologies that merited public support to market. And I'll just finally list them, and then we must get on to the panel discussion. And I began with, as so many experts do, with big data, high-performance computing, the software that you need to analyze very large data sets. And we have invested heavily, therefore, not just in the high-performance computing, but in the software you need to extract value. It's almost a rather vulgar race as to who can have the world's most powerful computer. At least we regard it as a vulgar race now, we're no longer winning it. But it is good to have the smart software that can extract the maximum value from your computer. So we invest in that. And incidentally, one of the reasons why the Square Kilometre Array is such a great project is it's going to create so much data, it's going to drive innovation in software and data science just because the data sets are so massive. So there's high-performance computing and data. Then my next 2 technologies are both applications and examples of this. One is robotics and autonomous systems, which are only really possible once you can write multiple very smart software programs so that you can, for example, envisage a robot taking on sophisticated tasks. If a little old lady lying in bed wants to send a robot to the kitchen to bring her a packet of cereal, it's got to understand her voice command, it's got to be able to navigate its way to the kitchen, it's got to pick up the packet of cereal, it needs to have the right level of grip so it doesn't drop it and it doesn't crush it, it needs another software program to recognize which cereal it's picking up. So it's a lot of complicated software systems that make robotics and autonomous systems possible, and we're now getting very close to that. Then third on my list was satellites and space. Satellites both as sources of data, incredibly valuable information about the state of the globe, its environment, coming from satellites, and also very effective ways of transmitting data. If Australia were perhaps to have an issue of not enough people being connected to the broadband, and if that were a subject of live political debate at the moment, and if I were to comment on that, I might say you can use satellites to provide access to broadband services if putting fibre optic cable to every house is unaffordable and slow to deliver. So, but fortunately that isn't an issue that really arises, does it? So, high-performance computing, autonomous systems, and space. Then we turn from those which are broadly IT-related systems to this extraordinary discovery of the structure of DNA. And we celebrated last year in Britain the 60th anniversary of Watson and Crick walking into their local pub in Cambridge and saying to the rather bemused regulars there that they had discovered the secret of life. To be honest, that happens quite a lot in pubs across England. But on this one occasion, it was true. And they had discovered the structure of DNA. And what they had discovered was that it comes basically in digital form. So we have this extraordinary coincidence that just when we have the beginnings of the explosion of IT with digitization and the use of digital technologies, we discover, amazingly, that the code that shapes life comes in digital form, which is why in Cambridge they say the future is the convergence of dry and wet technologies. So my fourth technology on the list is synthetic biology, which is probably the most ambitious attempt using understanding of the genetic code to create new organisms with specific purposes and applying increasingly engineering techniques. So you can order a bit of DNA code and have it inserted into a gene. So fourth is synthetic biology. Fifth is regenerative medicine, and I was having some fascinating briefing on this here at this very university only an hour or two back. But on regenerative medicine, what we can do now through stem cell techniques are extraordinary. I have seen on the Petri dish in a laboratory in West London belonging to Imperial College of someone growing heart muscle cells on the dish. And when I look at them through the microscope, they were beating just like a heart. They had the same pattern. You could recognize that these were heart muscles. So I said, how does this happen? Is there a sort of Michelangelo moment when you put an electric charge through them and they suddenly start beating? And the answer is no. These are living cells throughout the process. And when the living cells are trained to become heart muscle and they go above a certain volume of heart muscle cells, they start beating collectively. Of course, the real challenges then are to use those in human treatments. The real challenge is to get them into a patient in time, in volume, reliably to treat a patient with heart disease. But that's a challenge that you are addressing here at the University of Melbourne and we're trying to address back in the UK. And then, although those two life sciences examples are human medicine, sixth on my list would be agricultural technologies, applying again those insights from the structure and the pattern of life, and guess most importantly there, of course, genetically modified organisms, GM crops, which are an important way of improving the performance of crops in hostile environments, but a very controversial technology in Britain. I don't know how controversial it is here. But it was brought home to me how controversial it was and how the case for GM had been lost when we had a great little experiment set out by our research council that sponsors research in GM, the Biological Sciences Research Council, at a science fair last year. And they'd set out on the table 6, I can't remember, they were tomato plants, pea plants, something like that, numbered 1 to 6. And they'd all been grown with the same amount of water and in the same conditions, the same amount of soil. And some of them were flourishing, vigorous, healthy pea plants. And the worst one was a sort of scrawny, manky, misshapen pea plant. And the question for the school kids is, which of these plants is the GM plant? And they all chose the ugly, misshapen, skinny plant must be the GM plant, because they knew GM was horrible, and so it must be the horrible plant. Of course, the correct answer was that the GM plant was the one that was flourishing and blossoming and growing. But the kids all assumed the opposite, which is what happens, which had brought home to me how rather an important argument had been lost. So that was my sixth one, GM. The last two on my list, which are, well, first was energy and energy storage, and the real challenge of ensuring that the world has efficient batteries that can preserve power more efficiently than the old technologies. We still in Britain, when our power stations are producing more power than we need at any one moment in time, we pump water up to the top of a mountain in Snowdonia, and when it's half-time in the football match on Match of the Day, and people go out to make a cup of tea, we let some of the water out from the lake at the top of the mountain. It charges through a turbine and generates electricity in order to ensure that everybody can have their tea at the same time. And that's an effective system, but perhaps a touch primitive. And it would be nice to have batteries that ensured as we shift increasingly to intermittent sources of power, wind power, whatever, it would be good to have efficient batteries on that scale, as well as having efficient batteries for motor cars. We're still basically on a technology developed originally in Oxford in the early 80s, mass manufactured and very profitably in Japan. So batteries and energy storage was my 7th great technology. And 8th on the list was advanced materials, the materials that we need in order to, increasingly we'll be able to design them for functionality. So those are 8 technologies which passed some important tests. There are areas where Britain had a genuine scientific capability. There are areas where there were businesses that could exploit them, and there were areas where we thought there was a global market. And all of them we are supporting through the Technology Strategy Board and other means on their slow, painful progress from the idea of the scientist in the lab through to the market. And we're backing them closer to market than we would have thought of doing even a decade ago, because we've looked behind the rhetoric in America and seen the reality, and we're up for it if they are. Thank you very much indeed.
Thank you very much, Minister. Now we have an opportunity for a panel discussion which will be followed, or will actually evolve into questions and answers from the audience. To complete my panel for the discussion, would you please welcome Professor Ian Chubb, the Chief Scientist of Australia, and Provost at the University of Melbourne, Professor Margaret Shiel. I've been thinking about how we start this discussion, Minister, and it may seem impertinent, but why are you here? Why have you come halfway around the world to tell us what's going on in England?
Well, I hope it's not what everyone in the audience is asking. But I would say there are 2 reasons. I mean, apart from all the obvious historic ties between Great Britain and Australia, which visiting today and yesterday, that I see are still very strong. There are 2 particular reasons why I'm in Australia. The first is that the Square Kilometre Array, and I'll be flying out to Perth and out to Western Australia to visit it tomorrow. I think the Square Kilometre Array could be one of the world's great science projects of the 21st century, and it is a project with which Australia has a crucial role alongside South Africa, and where I also hope we in Britain will be able to play a crucial role, particularly up at Jodrell Bank, which is where radio astronomy really developed in Britain and indeed globally immediately after the Second World War. So with Bernard Lovell and others. And I think if our three countries, with other partners as well, can drive this project forward, that'd be great. I'm hoping and intend to carve out some money from our science budget, our science capital budget, to back it. But it always helps if you can see what's going on, and I wanted to see exactly what was happening in Australia and get a sense of your plans before we announce ours. So that's one reason. And the second reason is that universities are also my responsibility in the cabinet back in Britain. And the two countries that have gone furthest in developing income-linked loans repaid by graduates to help pay for higher education are Australia and the UK. We've both gone through some rather convoluted policy changes en route. Interestingly, the policy cycles in our two countries have been very similar, regardless of the political persuasion of the party in office, which is humbling for someone who thinks these must be party political decisions. But seeing how the debate on higher education financing is going. There are lots of other reasons, but those are the two most important ones, and I think both of them have proved to be fascinating already.
It's central to your thesis is the failure of the old model of picking winners and instead favouring, in this case, 8 critical areas of research that you want to create more or less the seedbed from which that research can go forward and can be developed into logical products. What's the situation here, Professor Chubb? Do we have a similar idea of creating critical areas for backing in research and development?
Well, we have the idea.
Right. Could you elaborate?
So I'm very envious of a lot of what goes on in the UK. I've been there a couple of times recently to look at, for example, how the Technology Strategy Board works, which is not something we have. We've not had anything quite like that, certainly not anything like that on the scale. I'm an admirer of the relatively recent catapult centres, which I think have all the promise that you could imagine. I mean, I think the Minister in a speech of his that I read, not that particular one, but an earlier one, where he said, you know, they mightn't all survive, they mightn't all work well because you are actually taking a risk. And but really the intention behind them, I think, is really great, to build that bridge between the researcher, the industry, and in the UK, particularly in regions. And we don't have anything quite like that. We are probably edging close to it by transforming what started out as precincts, so-called precincts, and they might end up as something different. Well, they will end up as something different, but they might be closer to the sort of notion of the catapult centre. And I've been discussing with governments, because we've had 2 in the past 12 months, and 3 prime ministers, I think. The issue really is, are we going to be strategic about some of this thing? Because by contrast with Britain, we are only 22 million people. We don't have as big a research base. We can't actually do everything. We can't have quite the approach that we have inherited and continued in the way that we did. So I think it is a bit about being willing to identify areas where you have some competitive advantage, where you have some capacity already, where you have a serious national need, and ours would overlap with the ones that the Minister just announced. I mean, we have issues to do with energy and storage, and particularly with respect to transport. I don't know how many people in this room read the latest NRMA report, but we have 3 days of fuel in our petrol stations right now, and 87% of our freight goes by road. So an interruption to our capacity to import our fuel, 90% of which comes from outside the country, that sort of order, then we have some issues for us. And so there are issues like that that I think are of common interest. When we've looked at it and advised government, we have suggested that we do share enough to be able to work together. So I think likewise with the Minister and some of what he said and written elsewhere, the international linkages are actually really quite important in this, and particularly for a country our size where we are good at a number of things, we're not good at everything. We probably do try to do too much, but where we are either trying to do too much because of the scale here, we should be linking when it's important, and we should be linking where we share. So energy, I can think of advanced materials quite obviously, agricultural issues, and GM will always be an issue in Australia, well, an issue for a while in Australia. Big data is an issue for us. Space, I don't think we have a space policy really, but question of whether we should have one or not's another matter, but at the moment, if there is one, it's very small. So there are things that we share. Our interests we share, there is a culture that we share, and I think we can learn a lot. I would learn first the Technology Strategy Board. I would gather together some of the programs that are presently funded and give it to the Technology Strategy Board to operate in very much the way it operates in the UK. And I would turn some of what we're proposing into catapult centres of that type of organisation. And I think we would be likely to get advantage from it too. It's a risk. I think the Minister said that first of all they beat up on themselves, and we're good at doing that too. Probably better at it really. And we don't take risks, or we've become, I think, too averse to assessing and managing risks. So how you bring that together and how you do that with suitable partners from whom you can learn, I think is one of the keys for our future prosperity.
Professor Shield, earlier we were talking and you brought up that a key difference between the United Kingdom and here was the way we treat science infrastructure and the role that has to play in R&D.
Well, it was slightly broader than that, if you allow me to broaden it.
Please do.
In the point that I was making, and I'm sorry for those that have heard me make this before, but I think it's timely that we have a debate about the kinds of institutions that we need to support science and research in this country, and it picks up very much your point about how far the public sector investment should be. And if I can go back and slightly in our history to the period of sort of around 2000, 2001, when we started to ramp up investment in science and research through several initiatives, known as back in Australia's Ability 1 and 2, and then subsequent investments, there was a very strong rhetoric at the time that the way to get commercial outcomes and to get commercialisation from research was to put it in the hands of commercial people. And so we set up a number of centres and a range of initiatives where we put commercial boards or semi-commercial boards in to manage both infrastructure and research programs. And over the test of time, we put the synchrotron, for example, under that kind of structure. We put our National ICT Centre under that kind of structure. We put our Stem Cell Centre under that kind of structure. But if you actually look at where the real commercial wins have been, they've actually been in things like CSIRO, which had the longevity to see through the wireless technology through to defending the patents in the UK. When we've had various other, when we had issues with funding the synchrotron, it was the universities that stepped up to provide that, and similarly, the changes we made with the support for stem cells. So I think it goes exactly and sort of reinforces your point that we need to have longer, more stable funding in the public sector in some way, and then create what we need underneath that to create the kind of risks that we need to take. And the longer your funding horizon, the more risks you can take. Actually, it's the inverse of what they're thinking at the time, and so I think we've learnt from that, and we're in a position where we should take that forward as we address a range of critical infrastructure challenges. And I could go through all the other areas of infrastructure that are managed in that way. But it's the stability and the longevity of that the institutions, however you describe them, that's really, I think, going to pay off in the long run.
Minister, it sounds like you have a big tick from your Australian colleagues with respect to the idea of having a strategic plan for R&D in the United Kingdom. One question that I have, though, is if you've got a strategic plan that identifies areas of research that need support, what happens to the other areas of research? So what sort of support is there for, say, biodiversity research, climate research, astrophysics that aren't specifically identified? Is there still a mechanism by which they're supported under your strategy?
Yeah, because remember that when it comes to science, the science and research budget, our aim is very simple and it's hard to achieve, but for a medium-sized economy, still to be doing world-class research in as many different disciplines as possible. I mean, we may at some point in the future be forced to specialise, to say we can't afford everything, but at the moment we have a balance of research funding that's from the arts and humanities and the social sciences through the life sciences into physical sciences. So I'm absolutely not arguing for us to narrow down our options there. It's the opposite. It's still, and thanks to the extraordinary output of our scientists, for a relatively modest but stable budget of about £5 billion a year, we get world-class research in those areas. What I'm talking about is the next stage, when you're talking about shifting from science to technologies that are on their way to market, and where 20 years ago, under successive governments actually, the view was, we just do the upstream research, and once the idea has been generated in the lab, perhaps they might have taken out a patent, and then it's over to business. And I simply don't believe that that is a viable model. I think that is asking, as I said earlier, business to do things too early. Now, at that point, when you are talking about backing the commercialisation of technologies, you need substantial sums of money. And when I announced our 8 great technologies, the Chancellor came in and backed them with £600 million of investment. And for them, we're not going to absolutely sort of strangle at birth another technology, far from it. But when you are deciding where, this is going to need 100 million to be serious on its journey to market, there aren't that many technologies you can back with 100 million. But for the others, if they can find commercial partners or there's a friendly university, whatever, we're not going to extinguish it. But these are ones where we've decided to put extra money on a strategic basis. And going back to what you said earlier, actually, on picking winners, part of the problem was that governments had been so used to the idea you can't pick winners that they had stopped taking these kind of risky decisions. And I fully accept on that list of 8 technologies, in a decade's time, people might well be saying, whatever happened to synthetic biology? It never lived up to the promise. We all thought it was going to be a big deal and it wasn't. Or they still haven't found a battery that's an advance on the technology of the 1980s. Maybe, and in fact, I'd be very surprised if all 8 deliver. But I think some of them will, and it's worth a punt on all 8 of them.
Professor Chubb, another key feature that differs between the political culture around R&D between the United Kingdom and Australia is, in Australia we have a chief scientist federally, we have state chief scientists, many of whom are actually only part-time, whereas in the United Kingdom they have chief scientists, they have scientists and science advisors in every government department. They're more through the infrastructure, more broadly spread. While that would be, it would be covetous of us to desire to have that here, would that actually be practical, considering that really, we're talking about a R&D sector that's perhaps 1/6 the size of the Great Britain?
Oh, probably not, Paul. But the reality is a bit different. I think it's like the Minister mentioned, going behind and having a look. Within the Commonwealth, there are at least 4 or 5 people who carry the title Chief Scientist of something. So there's defence, there's agriculture, there's Antarctic. There might be some more.
Employment.
Employment.
Yeah.
Oh, yeah.
Yeah, remember that one?
What, Chief Employment?
Yeah, no. The Chief Scientist
Chief
appointed by the former Minister for Employment.
Anyway, there are a few. And we get together on a reasonably regular basis. One of the issues for the Commonwealth of Australia is that we have 170 budget lines supporting research and development in the federal budget. Now, not all of those are big and meaningful beyond the immediate moment for a departmental head who wants a bit of research done for a particular policy-related purpose. If you eliminate those, it gets down to still a very large number, and there are half a dozen departments that are quite sizable. So somewhere along the line, what we have to try to do is to get to understand actually what's happening, and then we can think about whether we prioritise in a particular way, or whilst defending the sort of basic research in areas that are not immediately obvious in priority terms. So I do spend a fair bit of my time and talking to the individuals with responsibility for science or R&D in the other Commonwealth departments. And with the states, we meet once or twice a year, and we have a bit of a talk about what's going on. But, you know, I'm getting to be an old man, and I know that you've got to do things reasonably quickly. And as a consequence of that, I get sick of sitting in rooms talking about things. And I've done it for most of my life. As I remarked the other day at the Universities Australia conference, I've sat in many academic boards, so I know precisely the definition of futile debate. And I don't like doing that anymore. I think that we've actually got to begin to accept the fact that we need to identify, evaluate and manage risk and be a bit bold and get past the notion that it's impossible to pick winners, because when you look at the Minister's 8 technologies in the paper, they are 8 technologies clearly described, but they're also fairly broad within, so it's not all locking it up behind one word or one phrase. There is a spread, and it covers research. There's a lot of research being done in these technologies through, as he said, to the more commercial end. And we don't do that. We're like Britain used to be, stopping early, worrying about the valley of death, complaining about it, wringing our hands, beating ourselves up, and then talking about it a lot for 20 years, you know.
We are good at that talking.
Yeah, good at talking. And writing reports.
I will be coming to questions from the audience momentarily. If you do have a question, would you please raise your hand so we can get a microphone to you, and we'll also be putting a camera on you. And I'll be coming to you in just a moment, Neil, because I just have one more question of Professor Shield, and that is that a feature of the R&D landscape in Australia, and it's also true in the UK, is that there is quite a heavy emphasis on that R&D being conducted in universities. Do we need to devolve out that centre of work from universities to either private institutions or to government institutions?
Well, you know, we if you look at the sort of government investment in research as opposed to the university's investment in research, it is actually quite diverse, and you know, so the CSIRO budget is much larger than the ARC's budget, which is funding research into universities. And we have invested quite heavily through R&D tax concessions and R&D tax credit into research in the private sector. And you know, the value of that investment, which is about the same as the research infrastructure block grants into universities in terms of the total quantum, is not really evident. A lot of it went into, you know, roads towards research labs in mines, and you know, and software purchases. So, I think what my point really was, and I mean, there's room for diversity, and we have also got, you know, we've got the Medical Research Institute sitting here, we've got CSIRO, we've got a range of other institutions, but the notion that we need to privatise this and we'll get a better outcome, I think, is flawed.
Okay, we have questions coming in from the audience. Well, let's start with Neil Byrne in the back row. He had his hand up first. If you can just wait for a moment, Neil, so I can ensure that we have a camera on Neil. Do I have a thumbs up? Neil, your question, please.
Minister, in the US, Republicans are not seen to be terribly science-friendly. And perhaps people are struggling to make the case for the role of science as a driver of economic development. We've got a new Conservative government in Australia. I think scientists are a little bit anxious, not quite sure where they're coming from on science. In Britain, your government clearly has a sense of science as a major contributor to economic development. How did that awareness arise? Is it that the Tory party is traditionally science-friendly, or is it that science organisations successfully made a case? How did you come to be such strong advocates?
Well, I don't think, in America either, I don't think it would be right to make it too much of a partisan issue. I would say in Britain it's a couple of things. Partly when we look around Britain at things that we are good at, one thing you do notice is that, amazingly, we are still very good at science. And not necessarily not just people born in Britain, but providing an environment where people from all around the world want to come and do science. I mean, I had the privilege of going to the Nobel Prize ceremony, and not by some strange omission to collect a Nobel Prize myself, but because as a British scienceman, I went in 2010 when there were 4 Nobel Prizes for Britain, but only one of the Nobel Prizes in medicine was for someone born in Britain. Christopher Pissarides, who got the economics prize, had been born in Cyprus but had made his career in economics at the London School of Economics. And Andrei Geim and Kostya Novoselov had been born in Russia, then worked in Netherlands, and then done their work at Manchester that won the Nobel Prize in Physics. So we're a great environment for science, and when you've got something you're good at, it's right to back it. That'd be the first reason. And the second reason is, we've been hit by the crash as badly, if not worse than anyone. We've had a really big fall in our GDP immediately after 2008. And there is an economic value to science. Now, you have to put this very carefully. It doesn't mean that every scientist has to be funded on the basis of some specific prediction of what he or she is going to do. And so you have to provide the autonomy for scientists to pursue curiosity-driven research. But nevertheless, in aggregate, having good science going on in your country is good for your economy. And it works in various ways. It increases your ability to absorb and understand the advances happening elsewhere in the world. It also makes us attractive for globally mobile R&D. We get more internationally mobile R&D coming to locate in Britain than anywhere else. So I think those 2 arguments you can make, and they are ones that I found my colleagues in the Cabinet, especially the Chancellor, George Osborne, very receptive to.
We have another question over here. Hang on, just a moment. I'll get a thumbs up from the cameraman, and off you go.
Minister, you've been a world leader in open access, really pushing forward that initiative, and also in the G8 summit with science ministers, you've also commented on open data. I wonder if you can talk a little bit about your initiative in that area. I'm obviously very aware that in the Technology Strategy Board, you've pushed forward the Open Data Institute and trying to push that forward. Can you talk a little bit about why you've supported that and how perhaps Australia could adopt a similar initiative?
Yeah, and this actually links to the previous question as well, because there's the economic historians still endlessly debate, why did the Industrial Revolution start in England? Why did it happen there? And there are various theories. A very contemporary theory that relates to our understanding of the world today is this book by Mokia called The Gifts of Athena. And the argument in that book is that 18th century England had a network of publications, learned societies, informal networks in coffee shops and elsewhere, so that when you made a technical advance, knowledge of that technical advance spread rapidly. In other words, we were a highly efficient information economy. And in the past, if someone had worked out a different way of operating a mill or something, it might very slowly have percolated through, but there wasn't an efficient information system for conveying it. And 18th century England, by then, as a free society with a free press and autonomous learned societies and printing, and we're about to celebrate the 350th anniversary of the publications of the Royal Society, had a very efficient information system. And that is relevant for science today. And my view is that part of the funding of science is to pay for the communication of science. And in the trade, in the debates about forms of access, that's gold open access. You say part of your research grant is to pay for your research to be communicated. And it's only gold open access that achieves the ideal situation that publicly funded research is available for everyone from day one. It's not hidden behind a paywall, it's available from day one. So that's my principle on the access to research findings. But perhaps even more important is behind the findings are the data. And I remember we had a discussion in London, I don't remember if it was the G8 Science Summit or some other occasion, and around that table there were the main public funders of medical research. And probably between them, the leading science, health, medical research agencies in the Western world, probably, say, lung cancer, I know that's a bad example, prostate cancer. They may have had tens of thousands of studies, hundreds of thousands of patients. And really, for medicine to advance now, all that publicly funded medical data should be in a machine-readable, comparable form, so that any medical researcher could access that data, of course, properly privacy and confidentiality protected. And the worry behind the open access debate is that there's too many different sources of data. What we're seeing balkanization in Britain, where individual universities have their own format for preserving their data, where different journals have different formats, where sometimes scientists might think that the bit of software code that he or she wrote to analyze the data was the most precious bit of property they'd got, and they weren't going to share that. And my view is if we can make available the data behind research findings, that is a resource that can then be used by other scientists and researchers. And that's the real prize. And that requires international agreement. And the Royal Society is leading that for us in Britain.
We have another question on the floor, right over the back corner here. Just wait until we've got a camera on you, please, sir. Thank you very much.
Minister, thank you very much for your list of 8 grand challenges. I imagine that many scientists would be in complete agreement with that list around the world. I'm interested in the internationalisation of those questions, and can Britain solve those questions on its own? Should it solve it on its own? Is it time to think more globally rather than nationally?
Well, mine was really mine was very much a technology push list. It was a list of technologies that were emerging. There is separately, indeed, a list of big challenges. And as these are general purpose technologies, in many ways, there's several different technologies that are relevant for the different challenges. You can kind of marry them up, but it'll happen over time. And it was very interesting when we had the presidency of the G8 last year. So we had a G8 Science Summit in London, and one of the items I put on the agenda was, let's go through the list of kind of global challenges and just refresh it. And what I learned from that day's discussion was that, of course, there were the ones we're already familiar with, energy security, environmental standards, demographic change. What came up on the list of challenges was a couple of life sciences challenges. I think what was significant was that I think there was a general view that first neurodegenerative disease was a big challenge especially for countries with aging populations. And secondly, that antibiotic resistance was a big challenge for medical systems. So those got pretty clearly added to the list of challenges. As to how, none of them, neither can the advance of the technologies nor the tackling of the challenges be done by one nation state. They absolutely do require international cooperation. And we know that our science publications that are co-authored with scientists from other countries are more highly cited, and partly because they're just better when you look at a problem through more than one perspective. And if I may say so, going back to your original question, we know that scientific publications co-authored between British and Australian scientists are 3 times more likely to be cited than papers by either of our scientists on their own, which is why international cooperation is a good thing.
We are coming very close to the end, I'm sorry, but I would like to finish with a comment from the Minister, if you would indulge me. I know you haven't been in the country very long, but I do know that you've been whisked around to see all sorts of Australian facilities. Have you picked up anything from us that you're going to take back and work into your strategic plan, into your thinking about R&D? Is there something we're doing right?
You're doing lots of, you mustn't be doing it. I mean, Australia's a great place and there's lots of exciting things happening here. I mean, today, just in the 2 universities I visited here at Melbourne, clearly really interesting and important stuff happening with neuroscience and understanding the brain, and one of the world's big centres for that. And then at Monash this morning, seeing very interesting technical developments in photovoltaic cells and trying to use new materials so that you can have photovoltaic cells that are highly efficient but are also more transparent than we're used to. So yeah, there's a lot of smart people doing world-class work here, and I've seen examples today, and I think tomorrow your site for the square kilometre array, I mean, that is absolutely fundamental science. This is trying to get radio signals from the very early years of the universe after the Big Bang. There was, it's going to sound slightly biblical, but there was darkness, and then after about 300,000 years, I mean, I'm a layman, but there was the age of reionization, when light and radio waves of a more conventional form emerge, and it's possible that from the deserts of Australia and South Africa, for the first time, we will be able to track back to radio signals from those very first cosmic events, and that is about as exciting as it gets, if you ask me.
And if I may throw in an extra point of interest for you tomorrow, Minister, you'll be within a stone's throw of the place where the oldest mineral in the world has ever been found. Oh, yeah. So that's another bonus to put into your CV for the tour. Yeah. Ladies and gentlemen, would you please thank my panellists, the Right Honourable David Willetts, Professor Ian Chubb, and Professor Margaret Shields.
Yeah, thanks very much.
I'd also like to thank the British Consulate for all the work that they've put into pulling together this discussion and arranging the tour of the Minister and his delegation to Australia. Also, thanks to the University of Melbourne for providing these facilities, and also thanks to my staff at the Royal Institution of Australia, because they've done quite a bit of work as well. Thank you all very much. Go safely.